what I want to do is look at what does the magnetic field look like for an electric dipole that's moving. So if you have an electric dipole, it looks something like this. The field lines coming out one side and going back in the other side. And this is characterized by what's called the dipole moment. I'm going to call that the vector P. And the electric field for an electric dipole with moment P is 3K. Let me get my cheat sheet. 3K, okay. Dot r hat minus P over r cubed. And what I'm interested in looking at is when the dipole is moving parallel to the dipole moment. And basically the dipole is moving just parallel to its own moment vector. What does the magnetic field look like? And so what I'm going to do is I'm going to transform the electric field. So my magnetic field initially is 0. So I'm going to transform these fields into what they look like in the new reference frame, in the moving reference frame. And so if I want my dipole to be moving to the right, I have to transform to a reference frame moving to the left. And if I define to the right as positive, then my new reference frame is moving to the minus. Right? So there's a couple quantities I have to define. My beta, which is my velocity divided by the speed of light, and then gamma is 1 over square root of 1 minus beta squared. So I need these quantities to do this transformation. Okay. Now what I'm going to do is sort of a trick here, but I want beta to actually point in the direction that I perceive the dipole to be moving. Right, which I want it to look like it's moving to the right. So I'm transforming to a reference frame that's moving to the left. So to get the signs to work out right, I'm actually going to do as if it's minus beta for the transformation, since I'm transforming to the opposite direction that I think I am. I know that's kind of confusing, but anyway, if I do that, then B prime is gamma beta cross the original electric field. Normally there'd be a minus sign right here, because if beta was positive, I'd be transforming to a reference frame moving to the right, and it would look like the dipole was moving to the left, which is the opposite way I want it to look like. So I changed that minus sign from beta. And the other thing I want to do is say that beta is much less than the speed of light. And what that lets me do is say that gamma is approximately 1. Because if beta, is much less than 1, beta is much less than 1 means that my velocity is much less than the speed of light. And so because if beta is a lot less than 1, then beta squared is even less than 1, which means this whole thing is approximately 1. This whole gamma right here. Now you can say, well, that doesn't really affect this too much, we can just factor out this gamma up here. Well, that's true for this, but the other thing I have to worry about is coordinate transformations if I'm going to do a proper transformation. And what that means is the coordinates change too. The fields don't, or the fields are not the only thing that change. The coordinates change in special relativity too, but I don't have to worry about that right now. And so if I say that gamma is approximately 1, then the coordinates stay pretty much the same. Right? Okay, so if I do that, and I'm moving parallel to the dipole moment, which means beta is parallel to P, and so B prime is equal to 3k p dot r hat beta cross r hat minus beta cross p. Right? And so what I did was, since gamma is 1, I don't have to worry about these r's changing, right? Because then there'd be a complicated relation with these r's and r hats. And so I'll make my life a lot easier in terms of coordinates to say that gamma is approximately 1. Now, if you notice that since beta is parallel to the dipole moment, this cross product is automatically 0, right? Because sine of 0 is 0. And I'm going to define an angle, theta, which is the angle between the direction of motion and my position vector, which is where r hat is pointing to, so that this cross product becomes beta sine theta. Okay. Likewise, this dot product here becomes just the magnitude of the dipole moment cosine theta. And so if I do that, I get 3k magnitude of dipole moment, magnitude of beta, and then cosine theta, sine theta, and then all of that over r cubed. Now, this is a vector, and to maintain that vector, I'm going to define an angular vector called, I guess I'll call this phi hat, which represents an angular vector around, perpendicular to the motion of travel, and actually encircles the motion of travel, or the axis of the dipole, so that, right, so beta points like this, and then I do the cross product with r, and so there's a minus sign here. Oh, no, there's not. That's because I did that. Anyway, okay, right. So that do beta cross r points like that. So that on the front side of this dipole moving to the right, I get a magnetic field curling around like this. Okay. Now, and the other thing is, you might notice, well, cosine times sine, what does that do? What does that do to all this? And I've already made a cheat sheet here. So I plotted cosine and I plotted sine from 0 to pi, right? 0 to pi, that's 180 degrees, so from here all the way around. And so from 0 to pi over 2, this function is positive when I multiply them together. But from pi over 2 to pi, it's negative. And so what that cosine times sine does is the magnetic field curls like this on one side, but like this on the trailing side. Okay, but that really makes sense. So if I redraw the dipole, right, as the dipole moves to the right, the field lines are apart here, and so as it moves to the right, if you look at a point there, it's as if the field lines are coming together. The electric field is actually getting stronger at that point. Right? dE dt is greater than 0. Right? It's getting stronger. And according to Maxwell's equations, right, then if we have a positive time derivative of the electric field, then we get a curl of the B field, right? So if it's increasing that direction, we get a curl around like that, around magnetic field on the leading side of the dipole. But on the trailing side of the dipole, the electric field is getting weaker, right? So on this side, dE dt is less than 0. Right? It's getting weaker. And so if it's getting weaker, then we have a curl around in the opposite direction. And so it shifts, between curling the magnetic field going around in the leading side and curling around and going, trailing side. The other thing I want to talk about is the momentum density of the electromagnetic field. I'll just call that little p here. Now that's confusing because the dipole one was p. I'll just call it A. So the momentum density is basically E cross B. Now, if I draw the components there of the E field, if you notice, so these are the B fields here. E cross B at these points, so E is up and B is out of the page here. Now down here E is down and B is into the page. So on this side the momentum density is pointed to the right, the same direction that the dipole is moving. So the field itself experiences a momentum that corresponds to the velocity of the dipole. And so if you look at the back side, so down, cross, right, is in that direction. Up, cross, sorry, now I'm confused. Up and up is to the right. So everywhere the momentum of the field is, in effect, corresponds to the momentum of the particle itself. Because the momentum of the particle is to the right, the momentum of the field is to the right. And going back to the transformation here, right, you see that as beta gets bigger, right, the magnetic field gets bigger. And as the magnetic field gets bigger, the momentum gets bigger, right? So it's all corresponds to, everything is moving basically to the right, and there's momentum and energy involved in all of that. So anyway, that's the magnetic field around a dipole, moving dipole. There you go.